welcome to the 7th Jedi lesson video. This is week 4B, and we're going to go over the first problem in our Wiley Plus set this week, which states, the drawing shows 3 flat coils, 1 square and 2 rectangular, each being pushed into a region where there is a uniform magnetic field directed into the screen. Outside of this region, the magnetic field is 0. In each case of the magnetic field within the region has the same magnitude and the coils being pushed at the same velocity, v, each coil begins with one side just at the edge of the field region. Consider the magnitude of the average EMF induced as each coil is pushed from the starting position shown in the drawing unit, in the drawing until the coil is just completely within the field region. Rank the magnitudes of the average EMFs in descending order, largest first. Alright, so we know that we're going to be comparing these images and then going and ranking them from largest to smallest magnitudes. So first I want to start, as always, by defining some of the variables that may be useful to us. So the first thing I want to define is our EMFs, which is seen by this very fancy character, which I'm not sure if I could draw, but that's that. So this is induced electromotive force, which is an EMF, and that's a voltage generated by a changing magnetic environment inside the conducting loop. And the SI unit for EMFs are used by volts, which is a capital V. Then I do want to define our magnetic field, or B field, which is a field that exerts magnetic force on moving charges here. And right now it's uniform and directed to the screen. So we can see that through these X marks here. That's our B field. And the SI unit for B field is Teslas, which is a capital T. And then, as always, we have our velocity, which is represented by meters per second. We have our length dimension, which is represented by meters. And then we have area, which here it's square meter or meter squared. And then our magnetic flux, which we'll see in a second, is shown like so. This is magnetic. And it's measured using Webers. And then 1 Weber equals 1 T times meter squared. Okay. And then last but not least, we have time for the change in time, which is delta T. And SI units for time are seconds. Okay. All right. So the formulas that are important to us here in this equation, in this problem, are going to be the law of induction, which is our EMF average. This. And then we have time too, okay? And then we also have, since each coil starts outside of the field, which we can see in our images, then that means that we have our initial is going to be 0. And then that can be seen through this equation. That's supposed to be times for total area. And then the time it takes to completely enter depends on the width of the coil, which we're going to model using this equation, our delta T, width of the coil over velocity, okay? All right, and now we're going to calculate the total area, the time, and the EMF for each of our scenarios here. So we're going to start with coil A, which is here. And we know that the total area, we have this box. I'm going to do A in a pink color. Oh my goodness. Okay. So, for example, A, we have a box here with L here, and it's going through this field, this B field, with the velocity pointing to the right. So first we're going to find our total area, which we know we have L here, so it's going to be L times L equals L squared. And then our change in flux is this equation here, which is B times A total. Okay, and since we got our A total, we know that's L squared. We're going to plug that in. We have our L squared times B. And then now we're going to use our time equation, which is delta T equals the width. The width is L over V, seconds to enter. And then to find our average EMF for A, we have the B times L squared, because that's our total change in flux, over our time, L over V, equals B times L times the velocity. Alright, so we have this. And then now we're going to model it for our second image, which is B. And I'm going to use this green color. Okay, so for B, we have a rectangle. If I remember correctly, let me go check my image. Yeah, okay, we have a rectangle, and we have L here, and then this is 2L. The velocity is also pointing to the right, and we have our B field here. Okay, So we have this, and our total area is going to be RL times our 2L, which results in 2L squared. Our change in flux is going to be V times 2L squared. And then our time is going to be L over V seconds. Then our average EMF for B is going to be our B times 2L squared, which we got from our total change in flux, over our time, which is LV again, equals 2 times B times L times the velocity. And last but not least, we're going to do coil C, which I'm going to represent with the yellow, because here. Let's calculate this. We have another rectangle. This rectangle is facing this way, I believe. We have 2L and L here. Yeah, and then the velocity is pointing this way. Then we have our B fields that it's going through. Okay. So now that we have this, same thing, we're going to find our area. 2L times L equals 2L squared. Plug that into our total change in flux. And then plug that into our time. And then lastly, find the average EMF for C, which is B times 2L squared over 2LV equals B times L times V. Alright, so now that we have this, we're going to go ahead and compare it with the other answers that we got. So here, for simple terms, I'm going to write it like this, 2BLV and BLV. Alright, so let's look at what we have. We have BLV for A, 2BLV for B, and BLV for C. So both A and C are identical, so we have a tie there. And then B is an outlier. So then we know that B goes first because, remember, we're ordering the magnitudes of the average EMFs in descending order, so the largest first. And since it has a 2 in front, that makes it larger than having a 1 in front, right? So we have B, or the EMF of B, and then the EMF of A and EMF of C are tied. Perfect. So this is our answer, and we're going to check it. And that checks out. Okay, moving on to the second problem of week 4B homework. We have a long vertical straight wire carries a current I. The wire is perpendicular to the plane of the circular metal loop and passes through the center of the loop. The loop is allowed to fall and maintains its orientation with respect to the straight wire while doing so. In what direction does the current induced in the loop flow? So first, let's define our variables. We have our current is I, and the SI unit for current is amperes, which is represented by capital A. We have the magnetic field vector, or the B force, which is SI units, we know are Teslas. Area is represented by our meter squared. Then we have magnetic flux, which is measured by Webers. And then now we're going to get to the problem. So we know that using the right-hand rule, we're going to go ahead and set this up for this problem. So our thumb needs to point up in the same direction of the current. So we have this. This is our pole here. Okay, and it has a current I. So my thumb is going to be pointed up as well. Okay, and then our fingers are going to curl around the wire. So they're curling around the wire. They go like that, right? So we're going to go like that, okay? And that shows us that the magnetic field lines are horizontal circles centered around the wire. So then we know that the area vector also points straight up, and I guess we didn't know that, but anyways, because the magnetic field lines are just like going against or sliding along the surface of the loop instead of going through the loop like this, then the magnetic flux through the loop is also 0 at the start. And so then we know that no current can be induced. So then because of all of this, then the current, there's no current induced from this situation. So then our answer would not be like, it would not be that our current is going around this way, nor is it going around this way. There's simply no current being formed through this because our metal here is not going through the loop here. So then the correct answer should be C, or the third option, and we're going to check that. And that's correct.